Good morning. Waiting for a few more viewers. All right, cool. I'm at 15. Um, so a couple of announcements. Uh, your final is live, so you can take it now if you want to. It is due at 11:59 p.m. Next Friday. You have two attempts. It's 15 questions. Um, they're let's see. You get 200 minutes for each attempt, something like that. I don't think it's going to take anywhere near that long, but yeah, I double checked it for typos and stuff like that. I think it's good. Um, as far as late work is concerned, if you have any quizzes that you missed for any reason, uh, you need to turn those in by Wednesday in order for them to be considered. Um, so And let's see. I'm not going to have office hours next week because it's not homework based. The final is supposed to be something you do on your own. All right. So let me get started. I am going to review a couple more topics today, and I'll be finishing up my review on Monday. Okay. So, first thing I wanted to talk about today is momentum. So, momentum is a vector, and it is the scalar multiplication of the mass with the velocity vector. Okay? Your total momentum is going to be the vector sum of the individual momenta. Um, so the reason that momentum is important is that in a collision, the total initial momentum is going to be equal to the total final momentum. There's a question in the chat that I'm going to answer during the Zoom room today. So ask me that again during the Zoom room. Okay. So in a collision, the total initial momentum is equal to the total final momentum. So we use that to solve kind of like two types of problems that we sort of focused on this year. We focused on completely inelastic collisions. Okay. Um, and a completely inelastic collision is where we have the objects collide and stick together. So what that looks like, the momentum conservation equation for that is going to be, here's the initial momentum, and then afterwards they're stuck together. So they basically act like a single object. Okay. And so the mass of that object is going to be the sum of the two masses. So we have m1 plus m2 v final. So you can calculate the final velocity or whatever you need to calculate from this equation. And so in a completely inelastic collision, energy is the amount of kinetic energy changes because it might be turned into heat. So let's suppose you wanted to calculate how much energy is released or how much is dissipated. Your initial kinetic energy is going to be 1/2 mv1 squared plus 1/2 mv2 squared. Your final kinetic energy is going to be 1/2 m1 plus m2 v final squared. Then you would take these and you would subtract them, and that's going to tell you the amount of heat. Okay. So, and then we also talked about one-dimensional elastic collisions. Okay. And so for a one-dimensional elastic collision, we have that kinetic energy is conserved in addition to momentum. So our equations are m1v1 plus m2v2 initial equals m1v1 final plus m2v2 final. Okay. And then, so this equation expresses momentum conservation. And then we also have kinetic energy conservation, which is going to be 1/2 m1v1 initial squared plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared plus 1/2 m2v2 final squared. So this is going to be a system of equations for v1 final and v2 final. Okay. And so it's not a very fun equation to solve, but it is a useful type of problem. I want to emphasize that this second equation is only going to be true for elastic collisions. We went on to define impulse, which is denoted by J, and it's equal to the integral of the force that is acting on the particle with respect to time, dt, from t initial to t final. Okay, and the thing about impulse, oh my gosh, I went to sleep at like 2 a.m. and I don't know why, I just couldn't fall asleep, and so I'm really tired today. The reason that impulse is important, or one of the reasons why impulse is important, is because the impulse due to the net force, so if we made this the net force, is equal to the change in momentum of the object. So impulse is related to change in momentum. So that's a brief review of momentum. The next topic I wanted to talk about is circular motion. All right. So in circular motion, you have a an object moving in a circle, you could have a horizontal circle or a vertical circle. But in any case, whatever the form of the circle, the velocity is going to point tangent to the circle, and the acceleration is going to point in towards the center of the circle. So for that reason, it's called the centripetal acceleration. Centripetal means center seeking. So we learned an equation, we derived an equation actually for the size of the centripetal acceleration, and it's v squared over r. Okay. If we want to write that in terms of the period is denoted by t. We could write it as 4 pi squared r over the period squared. Or we could even write it in terms of the angular frequency omega, and it would be omega squared r. So that's the centripetal acceleration. Now, Newton's second law is equally valid for circular motion as it is for linear motion. So we could have, net force equals m v squared over r. So that would indicate a Newton's second law being used in circular motion. And in that case, this would be called the centripetal force. All right. So let me talk about some of the types of problems that we solve for circular motion. So one type of problem that we talked about was horizontal circles. And in particular, we discussed banked turns. So for a horizontal circle or a banked turn, if we looked at the circle, we haven't. If we look at it from sort of like a 3D perspective, we would have the object is moving in a circle. So here's the circle. We're looking at it from a 3D perspective, so it kind of looks like an oval. And so the velocity is going this way. Okay. If we wanted to look at it sort of from a rear view, you would typically have, so here's the circle, so we're looking at it edge on, and here's the object. It's got mg going this way. It's got some other force, I'll just call it F, going that way. The acceleration, because the object is right here, the acceleration is towards the center of the circle. So it's going to be in this direction. Okay. Now, if we were to do Newton's second law in the y direction, that has got to be equal to 0. Okay. Because it's a horizontal circle. It's not moving up and down. It's moving side to side. Okay. So that would mean that the y component of this force, so we have F sub y minus mg equals 0. In the horizontal direction, we have net force in the x direction equals m v squared over r. All right? Because it is accelerating in the horizontal direction, and that horizontal force is just going to be the x component of this force. All right? Using trigonometry. So we have these two equations that we can solve for whatever we need to solve for. All right. We talked about vertical circles. Okay, and so in a vertical circle, those are a little bit trickier. So a vertical circle is something like this, or like this, I should say. The reason that that's tricky is that gravity is pointing downward. Okay, whether you're at the top of the circle or at the bottom of the circle. Okay. But the acceleration is going to change because if you're at the top of the circle, the acceleration points down towards the center. But if you're at the bottom of the circle, the acceleration points up. Okay? And typically in vertical circles, there are more than one force involved. So you have a, maybe a second force, which I'll call just F, like that. So your Newton's second law at the top of the circle is going to be, F minus mg is the net force equals minus mv squared over r. All right. Because the acceleration is downward, whereas at the bottom of the circle, it's F minus mg equals plus mv squared over r. All right. And so another little trick that we introduced is that sometimes the velocity is not given, but it's actually calculated from conservation of energy. So a good example of that is a kind of like Tarzan swing kind of problem, right? Where you have something that starts here at rest and then it undergoes a quarter circular arc, okay, and the radius of that is r. And so maybe we want to know what is the tension in the rope or something like that at that point. Well, we would use energy to figure out what is the speed at that lowest point. So our energy equation would be mgr, because it starts out at an elevation of r, equals 1/2 mv squared. Okay, and then if we do a, so that comes from conservation of energy. Then if we do a Newton's second law at the bottom of the circle, in this case, the random force is going to be tension, right? So my Newton's second law is going to be tension minus mg equals mv squared over r. And so I can see that I have mv squared here, so I can plug in for mv squared there, and I can solve for the tension. Okay, so we're combining vertical circles with energy considerations. As far as, and then the next thing we discussed was gravitational fields and orbits. The formula for gravitational field is G equals big G times the mass below over r squared. So what do I mean by the mass below? So by the mass below, like what if you were talking about a planet? Okay. And you are right here. We want to calculate the gravitational field at that particular location. Then what we would do is we would just sort of like, boom, we would sort of shade in that region right there. And whatever the mass of that region is, that is the mass below. Okay. And then r is the distance from the center. So this would be r in that case. Big G is equal to 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. So this is one way to calculate the gravitational field. The other way is to do it by integration. And so if you do it by integration, it's going to be the integral of g times lambda of x dx over r squared. Okay, because remember, lambda times dx is actually dm. All right. So once we have the gravitational field, we can calculate the gravitational force on an object. And the formula for the gravitational force is just mg. All right. So where little m, so little m and big M are different things. Little m is the mass of the thing feeling the field, whereas g is the field that the thing experiences. So these are two. So little m and big M are two different things. Big M is the mass that creates the gravitational field. Little m is the mass that experiences the gravitational field. So that's how gravitational field results in motion. So then we started to talk about orbits. So if we do, net force equals mv squared over r, and for the net force, we use the gravitational force. So if gravity is the centripetal force, then what we would get is what's called Kepler's law. Gm period squared equals 4 pi squared r cubed. Okay, so that's a really useful equation. If it has 3 unknowns, and if we know 2 of the unknowns, we can get the third unknown. So that this equation applies to a circular orbit. We also discussed gravitational potential energy. And so the equation mgy is really only true if you're close to the surface of the Earth, because this equation assumes that the gravitational field is constant. The real equation is negative big G m1 m2 over r. Okay, where big R is the distance between the masses, and then m1 and m2 are the size of the two masses. Keep in mind that it's a negative number, and so the fact that the gravitational potential energy is negative is indicative of the fact that gravity is a binding force. It pulls things together. Okay, so if you were able to separate two things out all the way to infinity, infinitely far apart, then R would be infinity, and you would get that the gravitational potential energy is 0. Okay, if two things are really close together, their gravitational potential energy is negative infinity. Okay. So again, this equation accounts for how the gravitational field gets weaker as two things move further apart. So we were able to combine this. So we used Kepler's law to get the speed of a circular orbit. So the speed of a circular orbit was square root of gm over r. And so we were able to get the total energy of a circular orbit, which would be kinetic energy plus potential energy. And what we found was that it was minus g m1 m2 over 2r. Okay, so yeah, we calculated the total energy. So from that, you could figure out how much energy is required to change the size of an orbit. Another application was this idea of escape speed. And so what we did was we assumed that something started on the surface of the Earth, um, you know, and then it is launched from the Earth with a certain speed called VESC. And if it has the escape speed, then it is going to slow down as it leaves the planet. But as it's leaving, basically gravity isn't able to ever bring it completely to a stop. And so it's just going to keep going at a slower and slower rate. And it never comes back down. Okay? So if you achieve the escape speed, you're going to go up and never come back down if you meet or exceed the escape speed. And so we did that with energy considerations. We said that the energy at launch has got to be equal to the energy at infinity, which happened to be equal to 0. And so from that, we were able to get that the escape speed is square root of 2 gm over r. So it's a very similar equation to the equation for a circular orbit, but they're different things. Do I have any more room elsewhere? I'm trying not to use another piece of paper. We also talked about the total gravitational potential energy of a system, which basically, if you want to know the total gravitational potential energy, you would sum negative g mi mj over rij. So this is the gravitational potential energy of a single pair, and you sum that over all possible pairs. Okay, so a good example that we did was a square, okay, which has 6 pairs. All right. Now, one thing about this that's kind of useful is we can calculate how much energy is it going to take to remove one of these masses. What if we wanted to take one of these masses and pull it away? Well, what we would do is we would calculate the total gravitational potential energy of this configuration, and then we would calculate the total gravitational potential energy of this configuration with that mass removed. And then we would say, well, the difference between these two must have been the amount of work that was done to remove the mass. Okay? So that's my review for today. Monday, I am going to review rotational motion and simple harmonic motion. And then that'll be all the stuff from semester 1, I think. And so, yeah, you guys will be ready for the final. You could take the final right now. So I will see you in the Zoom room, where I will reiterate some of the things I said at the beginning of the lesson, and then I'll probably let you go